NASA unveils a bold new plan to look for signs of life on other planets. NASA's Institute for Advanced Concepts is well known for funding outrageous astronomy and space exploration ideas. Since its relaunch in 2011, the institution has funded various initiatives via its three-phase program. However, just 3 projects have received Phase 3 financing so far. And one of them has recently published a white paper outlining a quest to get a telescope capable of detecting biosignatures on neighboring exoplanets by leveraging the Sun's gravitational lens. That Phase 3 designation comes with a $2 million grant, which went to JPL, whose scientist, Slava Tereshev, was the project's primary investigator for the first 2 stages. He collaborated with the Aerospace Corporation on this newest white paper, which presents a mission concept in more depth and specifies what technologies are now available and what has to be developed further. However, there are many notable aspects of this mission design, one of which is discussed in depth at Centauri Dreams. Instead of sending a massive vehicle that would take a long time to reach its destination, the planned mission would launch numerous tiny CubeSats that would then self-assemble on the 25-year voyage out to the Solar Gravitational Lens, SGL, point. That point is a straight line connecting whichever star the exoplanet is orbiting and anywhere between 550 and 1,000 astronomical units on the far side of the Sun. That is a massive distance, far more than the meager 156 astronomical units traversed by Voyager 1 in 44 years. So, how could a spaceship go 3 times the distance in almost half the time? It will just plunge, nearly, into the Sun. Using the Sun's gravitational pull is a proven and tested strategy. The Parker Solar Probe, the fastest human-made object, uses similar technology. However, with the mission's speed increased to 25 astronomical units per year, the estimated journey time is not simple. It would be significantly more complicated with a fleet of ships rather than just one. The first issue would be one of material. Solar sails, the mission's chosen mode of propulsion, don't fare well when blasted to the intensity of the Sun necessary for a gravitational slingshot. Furthermore, the system's electronics would have to be significantly more radiation-resistant than present technology. However, each of these well-known issues has viable answers under ongoing investigation. Another apparent issue would be how to coordinate the passage of several satellites through this agonizing gravity maneuver while allowing them to coordinate joining up to create a fully working spaceship successfully. However, the authors of the research believe that the 25-year voyage out to the observing point will provide more than enough time to reconnect the individual CubeSats into a coherent whole actively. A more accurate representation of an exoplanet may emerge from that unified whole, which humanity is unlikely to encounter short of a full-fledged interstellar voyage. If the mission proceeds, which exoplanet would be the most outstanding contender would be a hotly debated question since more than 50 have been discovered in the habitable zones of their stars so far. However, there is no assurance as of yet. The mission has no financing, and there is no sign that it will result in the foreseeable future. And many technologies would need to be developed before such a mission could ever be considered. But that is how such missions always begin, and this one has a more significant potential effect than most. With luck, we will acquire as clear a picture of a possibly habitable exoplanet in the next few decades as we are expected to receive in the even medium future. The research team deserves credit for providing the framework for such a concept in the first place.